Saxon Algebra 2, Lesson 32. Look, you guys, I haven't even started yet, and I already made a mess of my title. I'm so sad. Quotient theorem for square roots is our main topic for this lesson. Like 31, there's a short geometry section that we will look at in a minute at the end. It's not, that's the easier part. Well, let's get our algebra taken care of right away. Let's remember that when we are multiplying square roots, we can write this either way, right? We can put the pigs in the same house, or we can spread out the pigs and let them live in their separate houses. That's the glory of the three little pigs, right? They can be together in a house, or sometimes they live separately. It's fine. It's all good. This is also true of the pigs in terms of division. They can live together in a house with an upstairs and downstairs, or, you know, they can split out into separate apartments. This is like a townhouse, right? But we can split them apart or leave them together, whichever is more advantageous to us, right? So these are tools we can use to change the shape of the radicals however we want. Now, I'll tell you why we might want to do that in just a second. Let's look at the example. 32.1. Simplify square root of 3/7. Now, here's the drama. Mathematicians don't like radicals in the denominator. We have talked about that, right? And even though this is kind of like a fancy high-rise with fractional pigs, this is not gonna float. We have to fix that. So that is why, in this case, we definitely want to pursue this other option, right? Let's get them into their separate apartments, and then let's rationalize that bottom pig. So that our final answer, then these we can put together, 21 over, and remember, square root times the square root always equals the number back. Square root of x times the square root of x equals x. 2 pigs in equals 1 pig out. A couple different ways to look at that. All right, so now we're happy because we've got a rationalized denominator and all's well in the world. Otherwise, like with these two forms, one's not necessarily better than the other. It's just two options. Similar for this, we can go back and forth between these. We do want to end up with a rationalized denominator though. Okay, let's try another one that's slightly more complex. I say that every time, don't I? All right. Well, what are we going to do about this? The first thing I would like to do is rationalize each of these fractions, and then I'd like to add them. Technically, we could do it in another order, but this is more theoretically precise. So we're going to rationalize these first. That means we need to bust them into separate pig houses. I'm going to leave myself a little bit of room there, plus square root of 5 over square root of 2, right? So I've just taken them out of their townhouse and put them in separate apartments. Then I'm going to multiply each one by the bottom pig, top and bottom by what's on the bottom, because I want this to be rationalized. And this gets confusing because John often does this where he has the same number top and bottom, right? He uses reciprocals. So you just have to be careful because it gets a little head spinny. Now I'm going to get square root of 10 over 5 plus square root of 10 over 2. That is all rationalizing. Now we're ready to add. And in order to do that, I'm going to have to find my least common multiple. That's going to be 10, right? 5 and 2. And so I'll multiply this one by 2 over 2, and I'll multiply this one by 5 over 5. Let me scoot up so you can see a little better. And now this will become 2 square root of 10 plus 5 square root of 10, right? This and this, all over 10 because the denominators match now. And I can actually add that. So this will become 7 square root of 10 over 10. I can't reduce those wolves. My work here, and I can't reduce anything out of the 10, right? There's no way to simplify that. That is my final answer. Okay, so first we rationalize, then we add. Oh my gosh, let's do another one. You wanna? I hear you saying yes. I can hear your little squeals of glee. Because who wouldn't want to do another one of these? All right, let me just show you this in the book. John is doing a floaty thing. Look, he's making floaty whole numbers outside of these. No, no, no. I am not going to write this. This is drama. I'm going to write them more properly in this format, right? I'm going to make the whole number be part of the numerator, and then I'm going to make that little bottom pig live in his own little apartment instead of sharing a townhouse, right? But these floaty numbers really annoy me. So this is the way we can start. I'm not even going to copy it like that. So here's what we've got. 3 times the square root of 3 over the square root of 7 minus okay, so just take a look again. I took the floating number and I bumped it up to the numerator, and then I put each of those guys in their own pig house. Okay, so that's how I got from here to here. Now we're ready to do our 2 steps. Number 1 is to rationalize. Now as you get faster and better at these, you can start to minimize the amount of work you're doing. So I'm going to do square root of 7 times square root of 7 here. And then I'm going to do the 3's over here. And then I'm going to get this times this, pig times pig, wolf times wolf, right? So this will be 3 square root of 21 over 7 minus 5 square root of 21 over 3. And it's so tempting because these already match and they look so nice and you just want to combine them, but you can't because those flipping denominators are still drama. So now we're rationalized. That was the first step. Now we're going to add LCM. Okay, that's 21. So I'm going to do the same thing where I'm just going to jot little notes to adjust. This one I'll multiply by 3 over 3, and this one I'll multiply by 7 over 7. Again, these are expressions. It's not an equation, so we can't blow up the denominators altogether. Remember, you can do that with an equation. You can blow it up altogether. But with an expression like this, no equal sign, the best we can do is just keep mushing it and get it all into one big clump. All right, now I'm going to multiply. 3 times 3 on the top, that's 9 times the square root of 21 minus 35 times the square root of 21, and it's all over, this is 21 and that's 21, so I'm good, right? And now I can combine these two because the radicals match. 9 minus 35 equals negative 26 times the square root of 21 over 21. Nothing I can reduce here. Final answer. 21 I can't reduce either, right? Because I could cancel between these two. I'm multiplying here, so it's okay to cancel. And I can simplify this. And I might even, I might be able to simplify this and then that would make it cancelable. You know what I'm saying? You would check this number first, see if you can bring any pigs out, then see if you can reduce. But I'm right out of luck here. That's not gonna work. So this is my final answer. One more. 32.4. And again, John is making drama by the way he's writing this problem. Floating numbers, pigs in a condo. No, I won't. I refuse. 2 times the square root of 2 over 7, square root of 7, minus 5 times the square root of 7 over square root of 2. These problems, he does this flippy thing. They'll always turn out to be pretty cute, but at first it feels weird. Step 1, I'm going to write it down again. Rationalize. Square root of 7 times square root of 7, square root of 2 over square root of 2, right? So that'll be a number, that'll be a number. Combine the pigs, so it's 2 square root of 14 over 7 minus 5 square root of 14 over 2. Now we're rational. The second step is to add. Fix those denominators, squish them together. Our LCM is going to be 14. I'm going to squish up because we're down at the bottom. So this I'll have to multiply by 2 over 2. This I'll have to multiply by 7 over 7. All right, pigs times pigs, wolves times wolves. So it's 4 square root of 14 minus 7 times 5, 35 square root of 14 all over 14, right? Because there's my 14, there's my 14. Yay. And then this is negative 31 square root of 14 over 14. Can I take anything out of here? No, this is just 2 times 7, so nothing will come out, and I can't reduce here, so I'm done. Holla. So nice, right? Oh my gosh. Do you feel smart? That's really hard, you guys. It's very, very hard. So that's good news. Okay, we have one geometry problem and a lovely vocabulary word. But I'm going to save us most of the drama on this geometry bit. We're going to talk about congruency. Here's the thing. They were men back in the day. The dudes who developed geometry were kind of their own breed, and they had some of their own rules. I mean, the whole postulates and, you know, a lot of the words, their vocabulary was quite evolved. And they decided they needed a separate word for the concept of things being equal. Because when you're talking about geometry, you're talking about shapes rather than values. So in most parts of math, we say that values are equal. But when we're talking about lines or triangles or angles, we say that the shapes are congruent. So this is just the geometry dude's way of saying equal, all right? And they came up with, I don't even want to tell you that yet. Never mind. Let's not even say it. So we've talked about things that are being similar. Geometric shapes being similar, and that means that they're proportional. And we can use ratios to solve for them. But when things are congruent, they're just straight equal. So let me show you a problem, and you're just going to be kind of like, wait, what? How is this hard? And I'll say, I know. We have two triangles. We've got a marker like that, and we've got a marker like that. So we know that all three angles are the same, right? Grace, are you okay? Can you hear her barking? She's pissed. When she hears things go bumping around when she's sleeping, she gets really worked up. Okay, then we've got a bunch of information about the sides. Grace, it's okay. Good job. Thank you. Good job. You should never scold your dog for barking. Do you guys know that? Because that's like their job. Good girl. Good girl. Okay, so we look at these two triangles. We know that the angles are all the same. And we see that one of the sides, one of the pairs of sides, is the same length. Okay? What that tells us is that these two triangles must be congruent. okay? Because all of the angles are the same, plus one pair of sides. That tells us that they're congruent. Now, once we determine that the triangles are congruent, we know that once we know they're equal, we know that the sides are all going to be equal, and we know that the angles are all going to be equal. Now, in this problem, we're mostly concerned with the sides. We need to solve for x and for p. Grace, are you okay? What is it? So I'm going to try to figure out if I can say that this side is equal to this side, and don't ask me why I circled this one first. If these two sides are congruent because they're corresponding parts of congruent triangles, then they must be the same. 6x plus 2 equals 12x minus 4. Okay, so first I determined that the triangles were indeed equal, which I did by determining that all three angles were the same, and I had 2 out of 3, we know 3 must be the same, plus one set of sides. That was the topper. I had to get at least one pair of sides that match. Now that I know that the triangles are congruent, I can say, okay, if the triangles are the same, then we know these bases must be the same. So I can solve and get a value for x. Swimming, minus 2 minus 2 minus 12x minus 12x. I'm feeling crazy today, and I've been letting my fish go negative on me. So this is minus 6x equals minus 6. Oh my gosh. John, divide by minus 6, and we get x equals positive 1, right? Because the two negatives go positive. Well, that was kind of nice. Our job, by the way, was to solve for x and p. I don't think I said that. Now we've got our x. Now we can go and look at this pair and make an equation out of them. We know that 4x plus 1 equals p. And we couldn't do this before because you can't solve for two variables with one equation. But now we know that x equals 1. So we can rewrite this, right? X equals 1. So this would be 4 plus 1 equals p, which equals 5. Okay, so once we determined that our triangles were congruent, then we could just create equations saying that the two bits were equal. That is the geometry piece of lesson 32. Aren't you glad that that was so easy and so semi-fun? I enjoyed it thoroughly. Okay, that's all. 32, I'm gonna video chat with everybody on Friday, right? Between 12 and 3. If you are not gonna get to me in that time frame, if something goes wrong or you can't find your mom to borrow her phone or whatever, then reach out to me. Go find somebody who does have a phone and message me or something so that I know what's going on, okay? A lot of times, you guys, once I finish my time slot, you know, like my noon to 3, I have errands or other appointments or things that I have to go do. And so I take off right away, unless someone says to me, oh, I'm gonna be 15 minutes late. Can you wait till 3:15? And then I'll try to shuffle and make that work. So if you need to be late, let me know. Okay, that's 32. Goodbye.